Alright, so I'm sure you've seen hot air balloons flying around a lot in the spring and summertime. If you've ever been in a hot air balloon, you are a braver person than I am. I wouldn't go anywhere near those things. Anyway, as you know, a hot air balloon just tends to float up in the air. That's because of, again, the hot air. Alright, well, if you think about it, you have your air molecules inside the balloon, and typically you have the exact same amount of air molecules. You really don't add too many more. All right. Now to go up, what they do is they have this little flame thing here, and that flame heats up the air inside the balloon. Well, when the air molecules get hotter and hotter, according to kinetic molecular theory, molecules are going to move faster and faster, so you're going to hit the sides of the balloon a lot more, and the balloon will expand. All right. Remember we said Charles' law, as you increase the temperature, the volume is also going to increase. They're a direct relationship. All right, so the balloon's going to expand. All right, so if you have the same number of particles, which in a sense means you have the same mass, but the volume increases. All right, when you have the same mass but the volume gets bigger and bigger, what happens to the density? Same mass but bigger volume, the density is supposed to decrease. All right, now think about density of objects. You'd learned about this way at the beginning of the year. What floats? Objects with a smaller or lower density. Same thing happens with air. Air can have different densities, right? Even just your regular air. Hotter air should have a lower density because those hotter air molecules are spreading out more in that same volume. They get bigger and bigger, or they get farther and farther apart. That decreases the density. And since less dense objects float, just like in water, same thing in the atmosphere. Less dense air is going to rise. So that's why we say hot air rises. So as you keep heating up those air molecules and keeping those air molecules the same, spreads out the balloon, makes it less volume, the same particles, lower density. So that's what increases it. All right. If you've ever been on an airplane, that's typically how turbulence works. When you're flying in an airplane and you hit those turbulence bumps, all right, what's happening is you're hitting air pockets with different densities. So if you're flying in nice, warm air where the molecules are nice and spread out, you hit a pocket of cold air. Well, the cold air, those molecules are a lot closer together. Yeah, it's kind of like hitting a little bump. All right. So that's how density works, and that's how you have your hot and cold air pockets in different densities. Now, we have an equation for density of a gas, and it's derived from ideal gas law, PV equals nRT. Right. You can probably figure out, if you manipulate the equation, you can probably figure it out yourself. The way the equation works out looks like this. The density of a gas is equal to P, which is the pressure, M, which is the molar mass, okay, not just the mass, not just the moles, the molar mass, which remember you get that by adding up the individual elements in the compound. So that's molar mass over R, which is your gas constant, and your temperature, which is in kelvins. And when you combine them and cancel out units, this will be your gas density, grams over liters. I know typically you do grams over milliliters, but with gases, they usually do grams over liter. Still a legit unit for density because it's mass over volume, just like all other density units. All right, that's the equation we're going to use. So we're going to find the density of carbon tetrachloride, CCl4. So our equation, density, PM over RT. So we're going to find the density. So we have the pressure, which is 0.939 atmospheres. All right. So M, molar mass, so carbon tetrachloride. So C is 12.01 grams per mole. Chlorine, 35.5 grams per mole. Right, so if we add that up, I got, when I did it myself, I got 153.81 grams per mole. All right, so what's our gas constant? Our pressure's in the atmospheres, so we're going to use 0.8206 liters atmospheres Kelvin moles. And our temperature, 125. No, we don't put 125 in there. It's 125 plus 273. So if you add those together, you get 398 Kelvin. So we're going to put that here, 398 Kelvin. All right, now let's cancel units. The atmosphere is gone. What else we got gone? Kelvin, out of there. Moles are gone. All right, so what are units we have left over here? We got grams in the numerator, liters in the denominator. Sounds like a density unit to me, doesn't it? Grams over liters. So that's our unit, grams per liter. Now, do the math. 0.939 times 153.1 divided by the numbers on the bottom, and you get 4.42 grams per liter. So every 1 liter container, it's about 4.42 grams. So that's how you do density. Nice, easy equation.